So a couple of the easy ones we can knock off, right? What's the domain?
The real numbers.
Oh, sure. About the codomain. It's also the real numbers, right? That's what this tells me, the map from the reals to the reals. How about the range?
X is greater than 0.
No.
X equals 0.
What's the smallest value you get out of this? Negative 2, yes. So it's x greater than or equal to minus 2. How'd you find that?
Set equals to, or I factor.
Factor, right? And it's the minimum, so no, this can't be the right one. If we plot this thing, right, its minimum occurs at where 2x minus 4 equals 0. Yeah, that's it. That's at 2, actually.
Yeah, it's at 2. Not
That's where the minimum occurs at x equals 2. And what's the value at 2?
0.
It's 0. So it, no, so it just does touch. Okay. If you plot it on your calculator, you can see. So I'll believe that f of 2 is 0. If that's true, then the range, if that's true, this thing can't be true. Can't be true. What's the factoring?
X minus 2 times x minus 2.
It's minus 2, right?
Mm-hmm.
Yeah, so it is. It's that special case where it just touches the x's, just like that. And it's got a double root. Good. So what's f of 5? That should be trivial. Somebody computed it. 9, yeah. How about the image of the set 2, 3? Well, it's just the two values, right? It's just f of 2 and f of 3, which are f of 2 and f of 3, right? So what's f of 2? 0. Sure. You know that. And f of 3? 9 minus 12 plus 4?
1.
So that's the image of the set 2, 3 under the map. How about f inverse of 6? Well, to get that, I have to solve the equation x squared minus 4x plus 4 equals 6 and figure out all the values. Well, that's the same as x squared minus 4x minus 2 equals 0. Okay. And did anybody solve that yet? I don't think it factors nicely. You have to use the quadratic formula. And too low on the morals. So the pre-image of 6 is just 4 plus or minus the square root of 4 squared plus 4 times 2, right? So 16 plus 8 all over 2, right? Whatever those two numbers are, right? That solve this equation, which is really that equation. And the same thing, I'd have to solve the quadratic equation or factor twice to get the pre-image of 8 and 20. I simply solve f of x equals 8, and then solve f of x equals 20, and I would probably get two elements in this pre-image, the two roots of this equation, and probably 4 in that. So that's how we do pre-images. We have the answer, and we look to find what we plug in. That's equation solving. Okay. That's the idea. Let's move on to two other big topics to wrap up our new information for today. And Friday, that's all we'll do is play with these two sections, lots and lots of problems. So I'm going to get my original definition back here. I have a map that goes from the set A to the set B with some appropriate definition. We say F is 1, 2, also known as surjective, and will be responsible for both terms. Under what conditions? There's a real easy way to define this. If f of A, now we have this nice terminology, right? If the image of A is B. That's what it means to be onto. I hit everything. I get to everything. But that's not the usual definition, because it's not a very good working definition. So the more useful definition is if for every B in V for every element in the codomain, what do you suppose?
Exists on A and A.
Perfect. Such that, using function notation,
F of A equals B.
sure. That's the same thing, isn't it? It says that no matter which element B I pick, there's at least one A that sends me there. In relation notation, it's the same as saying, if I pick any element in B, there's a pair AB in the relation. Or in the diagram notation, if here's my set A and here's my set B, if this is little b, there's got to be at least one guy that sends me there, that gets sent there. So this is B with little a. There might be several, but there has to be at least one for every B in order for the thing to be onto or surjective. And that's an important thing. It means that my map gets everywhere. It covers everything. Okay, I think I can write the other definition here. F is 1-to-1, or injective if, this is a little touchier, the right definition is, I'll write the if again here. If f of A equals, A1 equals f of A2, then I must have, what do you suppose?
A1 equal A2.
Yeah. And as you learned in Math423, if I take the negation, not the negation, the contrapositive of this statement, I can equivalently say, negate this one, implies the negation of the other one. Or in other words, I never send two different things to the same place, right? In my diagram, this says if this is my set A, and this is my set B, this never happens, right? Because I have, here's A1 and A2, but the F of A1 and F of A2 are the same. This is ruled out when I'm 1-to-1. It means each element only gets sent one place. So that's 1-to-1 and onto, the definitions. Onto, for every B, there's somebody that sends me there. 1-to-1, I never send two distinct elements to the same place. Never send two distinct elements to the same place. Now we'll look at a couple of examples from linear algebra, I think, that highlight these ideas and maybe bring a few things back. If I have a linear transformation of vector spaces Rn to Rm, where I define the transformation by T of U is a matrix multiplied by U. Remember, that's the general idea of linear transformations. First of all, let's talk about the dimensions of A. Remember, when I do this with a matrix, I'm really forming a linear combination of the columns. Since the answer lives in Rm, the length of the columns of A must be m, so it must be have m rows. And in order to take a vector in Rn, right, I'm doing matrix times vector, I have to have n columns to dot with n elements of U. So that must be the dimensions of that matrix. To refresh linear algebra. Well, this is onto only if ax equals b has a solution. For every b in Rn, everybody in Rm. But if you remember from linear algebra, how do I guarantee solutions? Well, this only is true if I row reduce the matrix A, so this is the row reduced form, and it has a pivot in every row. That guarantees that I'll never get a pivot in the constant column, which means I can never have a no solution. Old linear algebra stuff you can look back to. But this says something important, right? If it has a pivot in every row, if I consider the number of rows versus the number of columns, what must be true if I have a pivot in every row? Can I have less columns than rows? No, right? Because pivots go diagonally, right, at best. So this must mean that the number of columns is at least as big as the number of rows. But the number of columns of A is n, and the number of rows in A is m. This says that n must be bigger. I must be going from a bigger dimensional space to a smaller dimensional space, or equal. Otherwise, I can't possibly be on it. And that makes sense. If this was R2 and this was R3, I couldn't possibly fill up R3 by mapping elements of R2. So the n must be bigger or the same, or this can never happen. Okay. Nice little reminder from linear algebra. Okay, one-to-one is even easier in linear algebra. Kind of nicer. This linear transformation is one-to-one. Only when, that is, if and only if it's both, right? It's one-to-one if AU equals AV implies U equals V. That's what we said one-to-one is, right? I can't map two different answers, I can't map two different things to the same place. But this has a nice, easy switchover. This says then if this is true, then AU minus AV must be 0, right? 0 vector, if they're equal. But matrix multiplication distributes over vector addition, or matrix addition. So that's true only when A times U minus V is 0. But this condition implies what about U minus V? Well, they're equal, so that's 0, right? And remember, that's really the definition of one-to-one in a linear transformation. If the homogeneous equation only has 0 as a solution, right? So there's an example of one-to-one and onto tests in a familiar domain. Okay, one more quick definition that will be a lead-in to Friday, and then we'll work on the homework and give you back your quizzes. Vector spaces are a real important example of these algebraic structures that we're going to be working with. Okay. This kind of goes full circle. This is my way of remember, right? What the Cartesian product is a set. Set of what?
Coordinates.
Almost, formally. Set of ordered pairs, right? Well, we're focusing on the set thing now, so it's possible to form a map from this set to that set. You've seen maps like this a lot before. What does this say? It says I send every ordered pair to something. Can you think of something you've been working with since first grade that behaves this way? I take in two numbers and output another one. What's the simplest way to combine two numbers? Addition, sure. Add behaves this way. This is what add really is, right? So plus takes a pair of numbers, 1 and 5, and maps it to their sum, right? What else behaves like this? Multiplication, sure. Times behaves like this. Lots of, these are called binary operators. So we usually don't write this, we write the notation as x plus 1, or x times y, or whatever. But this is a shorthand notation for a function from a cross a to a. That kind of completes our material, and I think you can probably stop the camera. And let's talk about the homework.